We're going to look at some examples where we are going to solve a Bernoulli differential equation. On the left, I've written down steps that we can follow, and on the right in green, I've written down the general form of a Bernoulli equation. Let's look at our first example. We have x squared dy dx minus xy is equal to minus y squared. This almost looks like a first-order linear differential equation, but notice that the y on the right-hand side is raised to the second power, which makes it a Bernoulli differential equation. The first thing that we're going to do is we're going to write this equation in general form and find n. Looking up at the right-hand corner, notice that the derivative is by itself. So that tells us we need to divide each term by x squared in our equation. This gives us dy dx minus 1 over xy is equal to minus 1 over x squared times y squared. And let's make a note that n is equal to 2. I wanted to do an example where n was positive, and then in our next example, n is going to be negative. The second step is to let u be y to the 1 minus n. So we let u be y to the 1 minus n. N is equal to 2, so this is y to the 1 minus 2. So this tells us that u is equal to y to the minus 1. I'm going to highlight that because we're going to need that. The third step is to calculate du dx and then solve for dy dx. That's so that we can change our equation to an equation in terms of u. Du dx is equal to minus y to the minus 2. I'm looking over here on the right to the highlighted expression. And then we have to multiply this by dy dx. Let's now solve for dy dx. So I'm going to bring that over here to the left. Dy dx is equal to minus y squared times du dx. Now let's go back up and look at step 4. We are going to substitute our expression for dy dx back into the general form of the equation. That general form is right here. Instead of dy dx, we're now going to have minus y squared du dx minus 1 over xy is equal to minus 1 over x squared times y squared. Let's now simplify this. Let's get the du dx all by itself. So we have du dx plus 1 all over x, and I'm going to write the y as y to the minus 1. And then on the right, we have 1 over x squared, because we're dividing by minus y squared. Now let's go back up and look at step 5. We are going to substitute y to the 1 minus n is equal to u into our equation. That's this substitution right here. Let's go ahead and write that over here. We have u is equal to y to the minus 1. That's what we're going to put in. So in step 5, we have du dx plus 1 over x, y to the minus 1 is now u, and our right-hand side is 1 over x squared. Notice that this equation is a first-order linear differential equation, and we already know how to solve this. If you need a review on solving this equation, I have a video on that you can watch. Let's go back up one more time, and let's look at step 6. For step 6, we have to solve our first-order linear differential equation for u, and then we have to make a substitution and get our solution in terms of y. So now we're going to solve this. To solve a linear first-order differential equation, you need an integrating factor. Our integrating factor mu of x is equal to e to the integral of the term that multiplies u. So we have a 1 over x dx. This is e to the natural log x, which is just x. We don't need the absolute value around the x because we're going to multiply each term by this integrating factor, and the plus or minus would cancel out anyway. So let's go ahead and let's multiply every term in this equation by x. This gives us x du dx plus u is equal to 1 over x. Our left-hand side becomes d dx of x times u. And then our right-hand side is just 1 over x. We're going to integrate both sides, and we get x times u is equal to natural log. Now we do need the absolute value of x on this one, plus c. I think we're going to need more space, so let's take this and bring this over to the next page. Now we want to solve for u. So we have u is equal to the natural log absolute x plus our arbitrary constant, and we divide that by x. Now we're all set to make our substitution and put our solution back in terms of y. We had that u is equal to y to the minus 1, and I'm going to write this as 1 over y because I think that's going to be easier. So our left-hand side now is 1 over y, and our right-hand side stays the same. Now we can invert both sides of the equation, and we get y is equal to x, all divided by natural log absolute x plus c. And that's the solution to our Bernoulli equation. Let's now look at our second example. This is one where our n is going to be negative. Our first step is to put our equation in general form and find n. This one actually is almost in general form. I'm just going to change the right-hand side, and I'm going to write this as y to the minus 2 so that we can see that n is equal to minus 2. Our second step is to make the substitution that u is equal to y to the 1 minus n. N is negative 2, so this is y to the 1 minus a negative 2, and this gives us that u is equal to y cubed. Now we're going to find du dx and then dy dx. Du dx, we're looking right over here on the right-hand side, is equal to 3y squared times dy dx. And then we can solve for dy dx. And we see that it is 1 over 3y squared times du dx. In step 4, we are going to substitute dy dx back into our original equation. So let's go ahead and let's write our equation again. We had x dy dx plus y is equal to 1 over y squared. This gives us x, and now we have for dy dx 1 over 3y squared times du dx plus y is equal to 1 over y squared. Now let's get du dx all by itself, so we're going to multiply each term by 3y squared divided by x. This gives us du dx plus 3 over xy cubed, because we pick up that extra y. And then on the right-hand side, we just have 3 over x. In step 5, we are going to substitute that u, write this down, u is equal to y cubed. And this will get everything in terms of u. Our equation becomes du dx plus 3 over x times u is equal to 3 over x. Notice that this is a first-order linear differential equation, and we can solve this using an integrating factor. Let's grab this equation and let's bring this to the next page. This leads us to step 6, where we can solve the equation. The term in front of the u is going to be used in our integrating factor. Our integrating factor mu of x is e to the integral of 3 over x dx, and this gives us e to the 3 natural log x. The 3 can come up top, and this is e to the natural log x cubed, which gives us just x cubed. Now what we do is we come back up to this equation and multiply every term by x cubed. This gives us x cubed times du dx plus 3x squared times u is equal to 3 over x times x cubed, so this is just 3x squared. We now combine the left-hand side, and this is the derivative with respect to x of x cubed times u. It's always your integrating factor times u. And then on the right-hand side, we just have 3x squared. Now we can go ahead and integrate both sides. The integral on the left is just the integral of a derivative, so we just have x cubed u. And then on the right, oh, it works out nice. We end up with x cubed, and then we have to add on our arbitrary constant c. Let's now solve for u. U is going to be 1 plus c over x cubed. Now we have to write this in terms of y. So let's recall from our previous page that we had u is equal to y cubed. So our left-hand side now is y cubed, and our right-hand side stays the same. Let's solve for y, and we'll take the cube root of the right-hand side. So our right-hand side is 1 plus c over x cubed, all raised to the 1/3 power. And there's the solution to our Bernoulli equation. And that's it. You now know how to solve Bernoulli differential equations by using a substitution to convert the equation to a first-order linear equation. You should now be all set to work through some practice problems on your own. If this video has been helpful to you, please consider subscribing to my channel. Keep believing in yourself and have a great rest of your day.